Well, to wrap up Unit 5, I'd like to circle back one more time to compact models. We've been using the MVS compact model as our guide to transistors throughout this course. And as we've indicated, this is a very strong physics-based model. We also indicated in Unit 1 that there's another type of compact model that is used for sophisticated, comprehensive circuit design. So I'd like to say a few words about that type of model in this last lecture of Unit 5. So if we're talking about circuit simulation, we'll have a core model, and the core model can be a strongly based physical model for the current voltage characteristics, something like the MVS model that we've been discussing. It needs to include a number of effects, series resistance, and we've talked about how to do that. It needs to include various leakage currents. We've done the subthreshold current. Could be considered a leakage current, but there are gate leakage currents. There are leakage currents at the drain. It needs to treat channel length effects. So our MVS model is really a model designed to explain short channel transistors. But a designer has available to them transistors of a wide variety of channel lengths, and the model has to describe all of those channel lengths. Modern devices confine electrons in very thin layers. There are quantum mechanical effects that have become important in the operation of the devices and that need to be accounted in compact models these days. There are geometry effects as we're going to different types of geometries, FinFETs and transistors like that. We need to treat electronic noise as well if we're doing analog applications. And we have discussed how we treat transport in a way that we can describe transistors all the way to their ballistic limit, all the way to their diffusive limit, and in between as well. So that's the IV model. But these devices are also switching, so there are transient currents. So that requires some type of, perhaps, capacitance model. And we need to develop a model that is strongly physics-based there too, that accounts for the various structures and electrodes and leads that are present, the intrinsic capacitances of the device, perhaps non-quasi-static effects as well. So we've been assuming that when we apply a voltage, the current instantly flows. But if we're operating at very high frequencies, there's some lag. It takes a while for the electrons to respond to the voltage. And that's a non-quasi-static effect that needs to be included for some applications as well. Well, that gives us our core model if we include all of those effects. So that's quite a large number of effects in addition to the ones that we've discussed in this course, which was focused on the basic operation of the transistor itself. But then the transistor is embedded in a circuit. The interconnects connect one transistor to another or one gate to another. They're critically important for the operation of the circuit and system. There are many other effects. When we operate these devices, we generate heat. That affects the parameters of the device and the performance of the device. Not every device is the same. There are slight mismatches between devices that need to be accounted for. The designer can lay out the transistor in different ways and will not always get the same IV characteristics, so those layout dependencies have to be treated. The process will be variable, and there will be some variability in the oxide thickness and the channel length and whatever, and we need to account for those variabilities so that the design works over the entire range of transistors and that might occur across a chip or from manufacturing lot to manufacturing a lot. The neighborhood of the transistor is also important. The various transistors and structures that are around the one of interest, they may generate stresses that influence the operation of the transistor itself. So those need to be comprehended as well. The reliability of the device itself can be modeled and is sometimes included in the model as well. There are some effects due to the substrate. There are various parasitic elements that are getting more and more important as the transistors get shorter and shorter. So there's quite a lot of effects and physical processes that must be comprehended for us to have a model that is suitable for designing sophisticated electronic circuits and systems. Now, you might ask, why should the core model, why does it need to be physics-based? Why can't we just generate a table of the IV data of the device. Why couldn't we take a polynomial to a high degree and fit the parameters in that polynomial to the measured data? Well, there are some reasons that people like the core model to be physics-based. One is that it relates the needs of the designer to the manufacturing process itself. So we speak the same language, oxide thicknesses, channel lengths, and things like that. These kinds of models generally result in the fewest number of model parameters, and that makes it easier to calibrate the model to the specific manufacturing process. It also provides the best basis for statistical modeling because we know the statistical variation of various parts of the manufacturing process, and then we can relate that back to the effect on the transistor itself. And manufacturing processes evolve over time. We go from one generation to another, but even within a generation, the process will evolve. And as the channel length may change, or the oxide thickness, or whatever, the compact model can be quickly and easily updated for the change in the manufacturing process. Now, a downside is that these kinds of models generally take longer to develop, but they have so many benefits that these are the preferred type of models these days. So you might ask, could we use the MVS model as our core model? Well, there are versions of the MVS model that are used for circuit simulation, but they tend to be used for simple circuits and simple applications, primarily in exploratory research and development to look at what the impact of this new transistor technology might be on an application. But it's not an industry strength comprehensive model for a number of reasons. One is that it's a model for short channel transistors. It does not describe long channel transistors, and it doesn't go smoothly from long to short channel transistors. And that's needed because we'll have transistors of different channel lengths in a typical circuit. There's a number of second and third order physical effects that we just haven't discussed and that it doesn't treat. It doesn't treat noise. It doesn't treat these various dependencies on layout. So there's a variety of effects that need to be comprehended and that are not in our basic, simple MVS model. Our model is very simple. We've been using it to illustrate the physical operation of the transistor and understand the operation. It's useful in analyzing measured data and extracting some useful information about what's going on in the transistor itself, but not for comprehensive circuit design. Now, BISM CMG, a multi-gate model, is an industry strength model. And if you look at that, we have 10 parameters in the MVS model. There are 200 parameters for the nominal transistor itself in the BISM model. And then there are additional 700 or so to describe all of the neighborhood dependencies of the surrounding environment for this transistor. So almost 1,000 parameters per transistor. But this is what is needed in order to do reliable, accurate circuit design with modern day technology. So these models are quite different from the simple model that we have been discussing. BISM is an industry standard model. You can learn more about it here. It's been around for some time and has been continually evolving and being updated as the technologies evolve and get more and more sophisticated. It's also been selected by the semiconductor industry as one of its industry standard models. Years ago, every company used to develop its own model. But as the models became extremely sophisticated, it just became impractical for every company to do its own compact model development and support and calibration. So the industry has focused on a small set of models that the industry shares and makes use of those standard models. And all of the commercial circuit simulation platforms that simulate these circuits will have available these industry standard models inside them. Now, let me just discuss a few of the issues that compact model developers have had to deal with, just to give you a sense of what's involved. So there are three basic types of models. There's a threshold voltage-based model, there's a charge-based voltage model, and there's a surface potential model. Let me just say a few words about what each of these is, a very few words. So threshold voltage-based models, we know what this is because we've talked about threshold voltage, and our MVS, a version of our MVS model is a threshold based model. This is a model from some years back that describes the above threshold behavior of a MOSFET. Let's assume that we also want to describe the below threshold behavior. Well, we could take a standard expression for the subthreshold current and use that below threshold. So this would be valid for VG below VT. But we have to make sure that these two models match up. So at VG equals VT, we have to get the same current from these two models. But more than that, we have to match their slopes and their second derivatives and their third derivatives. In fact, we would like the curve to be continuous and smooth to all orders of derivatives at that matching point. They should be C infinite continuous. Now, why do we need that? Well, as we discussed in Unit 1, the Newton-Raphson solution procedure used inside the circuit simulator requires us to take derivatives. So the derivatives need to be well behaved to get good numerical performance. But also, if we do RF circuit design, we worry about distortion. Discontinuities in derivatives will introduce non-physical distortions that are there. So we need to be careful to make sure that these models are smooth. Compact model experts use things called smoothing functions or connecting formulas that do this in a smooth and continuous way. And you can see how that's done if you take a look at this reference. Now, we're switching these transistors, so we may have a DC model. This is what we've been talking about. A DC model, we apply voltages, what DC currents flow from the drain to the source. We're also switching these transistors, so there are transient currents. Well, we can account for them by introducing capacitances. So, for example, there's an intrinsic capacitance between the gate and the source. There's one between the gate and the bulk, or the body. There's one between the gate and the drain. And these are voltage-dependent capacitors, so they're not simple capacitors. Now, there are other capacitors. There's a capacitance between the drain and the body, the source and the body. There are overlap capacitances between the gate and the drain and the gate and the source. And there are various other parasitic capacitances. But these are the main intrinsic capacitances, and we can illustrate that there's a problem. We can compute the capacitances. The capacitance from the gate to the source would just be the derivative of the charge on the gate with respect to the gate to source voltage. Now, when we draw circuit diagrams like this and we put a capacitor between them, the idea is that we have a simple capacitor that looks the same if we look at it from the gate or from the source. And to evaluate the current, we just take C dV dt. But since these are voltage-dependent capacitors, we have to pick some appropriate average voltage in order to do that. So that introduces some error. Another error is the fact that these are not simple capacitors. They depend on the voltage on two terminals. And because of that, they're non-reciprocal. The gate-to-source capacitance is not the source-to-gate capacitance. So we really can't draw them on a circuit schematic like this, which makes them look like they're the same from both sides. Now, the result of these effects is that when people started looking at circuits that were switching rapidly, they found that charge was not conserved. The charge at a node was not equal to the net charge that flowed into the node through the transient currents. So that's obviously not very desirable. Well, the solution was to base everything on charge. And we've discussed the mobile charge, how the mobile charge carries the DC currents. Well, that mobile charge changing with time also gives us the transient currents. And we can formulate in a physics-based way how those mobile charges depend on all of the voltages applied to the terminals of the transistor. And then we can compute the transient currents by differentiating those charges with respect to time. And if we do it that way, we can find that it's straightforward to conserve charge. So I believe all models today are done in this charge-based way, not by using capacitors. And finally, some models today are called surface potential models. So instead of being threshold-based, where we have to connect up above threshold and below threshold, you know that the IV characteristic is continuous when you measure it. Nothing magic happens at VT. It's just some arbitrary current, and we say above this current, we'll say the device is on. If we formulate everything in terms of threshold potential, then we can get a smooth curve. Now, we talked about how you do that below threshold and above threshold, so we would have to connect these two expressions, but it is possible to do it smoothly, continuously from below to above The resulting equations need to be solved in general numerically. People have developed clever techniques for doing it approximately, but if we base our charge models on the surface potential, then we can get a smooth model that goes all the way from below threshold to above threshold. If you want to see an example of a model like that, the PSP model is one example of a model like that. It's another industry standard model that is used today. Now, these are some issues that people discovered and had to learn and deal with. There are other issues as well. There's some very practical issues. One is that MOSFETs are symmetrical, that we have a source and a drain, but the source and the drain in most MOSFETs are identical. So if the voltage is changed during the operation of the circuits, the terminal that we identify as the source or the drain will switch. So if the voltage on terminal 1 is more positive than the voltage on terminal 3, then it's the drain. And if the voltage on terminal 3 is more positive than the voltage on terminal 1, then it's the drain. So the role of the source and the drain could be changing throughout the operation of the circuit. That can create a problem if the model is source referenced. And of course, we referenced everything to the source in our virtual source model because that gave us a very good physical insight into how the transistor operated. But we have to be careful in a circuit because the terminal that is labeled source might change as the voltages on the terminals change. So problems can occur when the drain to source voltage switches sign. So you can see it's possible to formulate models that are not source referenced, and here's an early example of a way that people did that. And there are various tests that people started running for models to see whether they did what they were supposed to do, that is, whether they were indeed symmetrical. And one is done here where we just sweep this voltage Vx from minus half the power supply voltage to plus half the power supply voltage. What that does is to sweep the drain to source voltage from minus VDD to plus VDD. We fix the voltage on the gate. So that switches the terminal that operates at the source as we do that. And we can look at the current as a function of Vx, the first derivative of the current, the second derivative, the third derivative, and we can ensure that everything behaves smoothly and properly as we do that in the model. So that's a very practical consideration. There are several others, and if you're interested in understanding the sort of things that people need to worry about to model circuits carefully so that the circuits they design will operate, there are a couple of references here that tell you some of those considerations. And if you're interested in diving deeper into the whole art and science of compact modeling and understand the history and the different kinds of models, there are two references here that can help you dive more deeply into compact modeling. Now, you may need to write your own compact model. Probably not to do MOSFET design because there are industry standard sophisticated models. But if you're adding to your basic electronic system a new device, you may need to write your own compact model. You should know that there is an industry standard language, Verilog A, for writing compact models. And you can write them in a way that they can be used by all commercial simulators. If you write your new model in Verilog A, then any standard commercial simulation platform can make use of that model. So if you need to do this, here are some good references to get you started on how to write your own compact model with Verilog A. Okay, so with that, I'll wrap up this very quick tour of compact models. Just wanted to make you aware of a few considerations should you need to use or even develop your own compact model for circuit simulation. They are the link between the manufacturing process and the circuit designer. They also are an increasingly important link in research because research on novel devices needs to be driven by the impact on an application. So at an early stage in your device development, you need to be thinking about what are the implications on circuits and systems. And for that, you can make use of less sophisticated compact circuit models. Developing a new model requires a good understanding of the underlying physics, but it also requires an understanding of how the circuit simulator solves the circuit equations so that you can make sure that the model behaves well in the numerical solution of the circuit equation. It also requires an understanding of the intended application. There's no, it's not useful to spend too much time in making your model 1% accurate on an aspect of the performance that doesn't have a significant impact on the application. You need to focus your attention on those aspects of the device operation that most affect the application that you're targeting. And if you're doing this, a lot of the lessons that have been learned over the years in developing good models for silicon MOSFETs should be applicable to other devices as well. So you should take some time to have a look at, understand what lessons people have learned and make use of that if you need to develop a new model. Okay, so we have discussed several different topics in Unit 5. It's really been a collection of different topics that you should be introduced to and at least be aware of. In the next lecture, I'll recap Unit 5 and just review some of the main points that you should take away from Unit 5.